Education is the most powerful weapon which you can use to change the world. Believing in this principle, welcome to Murray Lakshman Reddy Group of Institutions, providing world-class education and research facilities to help transform people's lives for the better. It is the brainchild of a visionary who conceived and promoted it in 2005. Meet the man, Shri Murray Lakshman Reddy, who ushered in the silent mission. A mission to provide technological advancement from time to time, with the aim of imparting education with global standards to enrich values with knowledge in students. Succeeding the paths of Shri Murray Lakshman Reddy, making education a positive experience. Shri Murray Rajashekhara Reddy, Founder Secretary, nurtured MLR Group of Institutions to win the pride of being recognized as one among top engineering colleges in Telangana for the past consecutive academic years. Situated in vast and peaceful area of 35 acres, students here tend to learn experimenting their live projects through centers of excellence, which is tied up with various industries. Spacious and comfortable classrooms, corridors, advanced laboratories, with equipped ultra-modern audio-visual technology auditorium, accommodating 1,000 plus audience, separate hostels for boys and girls. Each student is specially taken care for the provision of health facilities and hygienic food in spacious and eco-friendly canteen, etc. are salient features of MLR Group of Institutions. AICTE recognized MLR Group of Institutions accredited by NAC with A grade and has NBA accreditation for all programs. MLR Sports Complex and inaugurated by MLR Group of Institutions with most advanced multi-sports facilities like cricket stadium, badminton court, table tennis, billiards and basketball, etc. MLR Sports Complex organizes many national and international university-level sports fests by grooming every aspirant in competing national and international sports forums. Successfully achieved 50 gold medals, 13 silver medals and 16 bronze medals at various national and international sports events. MLR Group providing free admissions every year by supporting aspirant under sports quota with scholarships for the meritorious sportspersons to pursue their career in sports and opportunities in government sectors. To sharpen and extricate students' creativity and entrepreneurial skills, MLR Group has established Center for Innovation and Entrepreneurship with facilities like Social Square, Innovation Hub and Makerspace. The Makerspace is a technical prototyping platform for students' innovation and invention, which is loaded with ultra-modern equipments such as multimedia workstations, 3D printers, CNC machines, laser cutters, and thus provides stimulus for student entrepreneurs. The center has collaboration with various government and non-government ministries for raising seed fund to incubate student projects and startups. This center has developed 8 plus market-ready products and supported 11 plus student startups. MLR Group has set up Livelihood Business Incubation in association with Ministry of Micro, Small and Medium Enterprise (MSME) to promote new technology or livelihood-based enterprises. The Research and Development Cell has 12 centers of excellence in association with various industries and supports faculty and student research. It also has a track record of 25 plus funded projects, 700 plus SCI or Scopus journal articles and 35 plus intellectual property rights, and the progress continues. In preparing the aspirants to the real-world competitiveness, MLR Group of Institutions has introduced Indo-Universe Collaboration for Engineering Education IUCEE to introduce outcome-based student-centric education and Bloom's taxonomy-based teaching, learning and evaluation process, engineering projects in community services EPICS in association with Purdue University USA. Scope: School of Programming Practices to hone the coding and programming skills. Students' Platform for Engineering Education Development, SPEED, empowers the students to become a factor of change in engineering education and its effect on society and environment. Club Literary to organize MUN, TEDx Talks and Techno-Cultural Fest to uplift student communication and English skills to the global forum. MLR Library is fully loaded with diversified study material, books, national and international journals with dedicated digital library, along online subscription to massive open online courses, IEEE, Elsevier, Springer, ACM journals, etc. MLR assures the safety and security of the students. Its transport infrastructure includes modern and secure vehicles and strictly complied with RTA regulations with well-maintained safety standards. MLR Group of Institutions having faculty of nationwide experienced and renowned adjunct professors include the expert scientists of DRDO, DRDL, HAL, BHEL, SAE India, ECIL and JNTU, imparts education with pure practical inputs, offers courses in BTech, Aeronautical Engineering, Computer Science Engineering, Civil Engineering, Electronics and Communication Engineering, Electrical and Electronics Engineering, Information Technology, Mechanical Engineering, MTech with Aerospace Engineering, Computer Science Engineering, Embedded Systems, Digital Systems and Computer Electronics, CAD or CAM Engineering, Thermal Engineering, MBA courses. MLR proudly announces that till now, 75% of their students have grabbed the opportunities with average salary package of 6 lakh by holding premier positions in top-notch companies in global market. MLR relies always on the philosophy that intelligence plus character. This is the goal of education.
Good morning, everyone. Welcome to the session of Day 5 Faculty Development Program. So we have with us the guest for today's session, Dr. Ramesh sir. So can you please start your video? Ramesh sir?
Fine, yes, madam.
Yes, sir. So we have the guest for today's function, Dr. RameshBabu.V-Vibration, who is working presently with Vellore Institute of Technology. Dr. Ramesh has completed his Master of Technology in Machine Design, Mechanical Engineering from IIT Guwahati in 2009 and Bachelor of Engineering from SRKR Engineering College, Vishakhapatnam in 2002. He completed his Doctor of Philosophy from Vellore Institute of Technology in 2017. He is currently working as a senior assistant professor in Vellore Institute of Technology from March 2017 to date. His areas of research are vibration analysis of smart materials, smart and composite structures, design of automobile parts, machine elements, Internet of Things and mechanical engineering, and tribology of bearings. He is having a wide administrative experience as IIC member and Atal ranking institutions on innovation achievements from 2018, serving as a member of NAC Committee for School of Mechanical Engineering, served as faculty development coordinator and timetable coordinator and in charges for various laboratories at VIT. He has visited Guangdong University of Technology main campus under faculty exchange program and for discussion regarding research collaboration. He is presently guiding PhD on vibration analysis of honeycomb sandwich plates and acoustic analysis of sandwich plates. He has a number of international and national journal publications and patents on mechanization silver halide erector for printed circuit board film printing using programmable logic controller. He has received Honor Code Certificate, Technical Communication for Scientists and Engineers, IIT Bombay from 11 January 2016. He has delivered guest lectures at various FTPs and workshops throughout. With this brief, I would like to welcome Dr. Ramesh sir to the session. So welcome to the session, sir.
Thank you, madam. Thank you for your.
Yes. So you can start the session.
Good morning, all of you. Uh, the main motto of this guest lecture is, or lecture is, to give you the brief understanding of how the basics of the vibration and it's related with the composites and with the nano composites and the smart material structures. So, or that in the introduction, how the basic things, basics of the vibration are related, how we can relate to the composite vibrations or the vibrations in the composite materials or the composite structures. So that's what the basic idea today. And in the next session, I will discuss about how we can apply these one in a smart materials. What are the various smart materials and smart structures, and what are the various combinations we can make, like a nano composites we're talking. In the same way, can we make some other composites also? So those perspectives also we'll see in the next class. Basically, today morning sessions I'll discuss with the mechanics related to this, whereas in the afternoon session, the MATLAB sessions related to the vibrations as well as the composite, and a brief idea about how we can relate these things with the smart structures and smart materials in the MATLAB sessions. So as we everybody knows, before going to introduce on material characterization and the importance of today's discussion, I'll see. Yeah, as this is the stress strain diagram. Yeah, I'm writing these for the ductile material, where we know the various points. So these are the various points. Yeah, am I audible to you? Hello? Hello? Can anybody respond? Am I audible? Hello?
Yes, sir, you are audible.
Sir, you are audible.
Ah, thank you. So these are the various points as we know it. These are the proportionality limit, and then the upper yield point, then lower yield point, and this is the ultimate tensile stress. So this point is the ultimate tensile stress. Sorry. So this point is the ultimate tensile stress, and this point is the breaking stress. Breaking stress. Majorly, we know that from this point onwards, we'll go to the elastic limit, and then elastoplastic stage. Then it is in the plastic stage. So the components which are dealing with the design, mostly they are in the elastic stage, and sometimes it will go to the elastoplastic region. So this is the elastoplastic region, where this one is the plastic region. So this is the plastic region. So the members, as we know that there is a ultimate tensile stress. So sigma u. Sorry. So sigma u. Once any member reaches this ultimate tensile stress, so it will fail. But once the member is subject to a vibrations, before these ultimate stress itself, the member will fail. So for that, various theories are there. Then that analysis is called the fatigue analysis. But our major interest is in the vibration analysis. One part of the aspect is the structure analysis, where we'll talk about the member which is subjected to a stresses, and then which is these stresses are basically related with the motion, and if this motion is repeating itself, then due to this motion there is some frequency will be generated. Once this frequency is equal to the natural frequency of that particular system, the system will exhibit its maximum energy, where that condition is called the resonance condition. Due to this resonance condition, many the failures are occurring in a system, and always we need the systems to be run with a very high speed, and as well as the basic structures. Now we can see the composites. The composites perspective, we are replacing many of the metals with a composites. Then whether these composite materials can able to withstand these particular frequencies or not is the major analysis or the major area where we need to understand its structural behavior and how to assess these behaviors structurally. So and how these motions can be estimated, and how we can derive these governing differential equations, and after that how to solve these governing differential equations. After solving these, where we can predict its behaviors at a various stages. So that is the major agenda here for the today. So for that, the basic understanding of a vibrations I'll start, and then I'll couple these with a some of how the failures are occurring, and how in the composite materials or the composite structures we can make its governing differential equations, and how to solve this one and find its structural analysis. So that's what the major agenda for today. So we'll start with the introduction to the vibrations. A motion that repeats after an interval of time. So basically this is a any motion. So this normally we'll call this as a, so then it could be go both the sides, or it could be in a one side, and it could be a sine curve, square curve, triangular curve, or smooth curve. The motion which repeats, then we'll call this as a vibration. So there is a various types of vibrations are there: longitudinal vibrations, transverse vibrations, torsional vibrations. Then the example for this is a vibrating tuning fork, weight on the spring, a buoy on the string. So these are the three different examples for the vibrations. Any body possessing a mass elasticity is capable of vibration. So this is the major thing we need to understand. Any member which possesses some mass and elasticity is capable of vibrations. Then these, if you are connected, then normally it should be in a position of equilibrium. And these vibrations are sometimes are needed, and sometimes we don't. So what are these undesirable cases? Is where it will increase the stresses, energy losses, cause added wear, and various losses it will create. So in the same way, it is needed also in the case of a washing machines, in a mechanical shakers and sieves and other sorting devices and musical instruments. The stress relieving technique of a relatively recent origin makes the principle of this vibration. So where the vibrations are needed, then is the perspective where I can say these vibrations deals with the relation between the forces like stiffness, inertia, and damping, and oscillatory motion, where are these oscillatory motion related with the displacement, velocity, acceleration of the mechanical systems. Any dynamic system having the stiffness and inertia properties can have a oscillatory motion. The oscillatory motion can be a periodic or the random. So a periodic motion, the any motion that repeats itself after a equal intervals of time, as well as its acceleration is proportional to the negative proportional to the displacement. So these are the two conditions for periodic motion. A periodic motion can be solved as a series of sine and cosine curves, and a simple harmonic motion where we can see these displacement, velocity, acceleration, and these curves. And here you can observe where the acceleration, which is proportional to the displacement, but only with a minus and omega scale. So then we will come to one practical aspect where our observation started at this particular place, and the systems are a behavior at a starting point here where there is a zero amplitude and it went to the maximum. So once we take this as a simple harmonic motion, then x equal to a cos omega t, where cos, actually to start with this point, cos is a max, and we can give like here, already we have seen here, like sine is started here, then cos is here, then sine in a negative direction. The same way, it the equation x equal to a sine omega t satisfies the two condition called uh, period condition as well as the acceleration. So both the condition, then obviously the same x equal to a power a e power I omega t also satisfy these both two conditions. So that's why we can represent these periodic motions form of a sine curve, exponential curve, and a cosine. So this is a phi is a called a phase. That phase I will discuss in the next one. So once our point of reference, and its displacement initiation, where x equal to a cos omega t, the displacement initiation will be a cos 0 equal to 1. So where there is only a will be there, so cos will be 1. Then if both are same, then need not to add this phi called the phase angle. But here in this case, our point of observation starts from here, whereas the max amplitude, the initial condition started just before this. So then this is a phase angle, how much angle is difference, that angle need to be included. So then only we can properly estimate what is this displacement in the mathematical terms. So this is the phi, this is called the phase lead, and then the phase lag, where maximum our point of reference is here and its maximum is after the particular point. Then these are the phase differences and vibration characteristics. As we already see now, the inertia, elasticity, these are the two major elements. The inertia, normally this is a mass, and elasticity is represented with a K. This stores the potential energy and it stores the kinetic energy. Then the realistic addition called the energy dissipation. The symbol we'll use for this energy dissipation. Normally we use damping coefficient called as C. And then the ingredient, mass M and stiffness K and realistic addition C. So this is a combination for a one structure. This is a representation of a vibration modeling. Let us say this M undergone certain displacement called X. So this is just a model. And once we get these models, then how to solve these general equation of motion by taking a free body diagram of these particular masses and K and C, Newton's second law, or by D'Alembert's principle, or we can use the work energy or virtual energy method also we can use, or virtual displacement method also we can use, and then Lagrange equation and the Hamilton's principle we can use for solving these particular equations of motions. So what are the various causes of these vibrations? Is a major unbalance, and then the misalignments, and the parallel is called the parallel horizontal and parallel vertical, and angular horizontal and angular vertical. So these are the various misalignments. Then looseness can cause the vibration in both rotating and non-rotating machine. The looseness is often due to the excessive clearances, loose mounting spoles, and mismatched parts, etc. Then these are the wind-induced vibration or self-induced vibrations. So in the perspective of these flows, this is one incident where the total observation or the analysis of the vibrations have changed. This is called Tacoma narrow switch, and November 7, 1940. So these due to the wind-induced vibrations. So amplitude of oscillation has reached here the 14 feet. Then here the initiation of the joint failure has started. Then it slowly collapsed. Total structure. So after these onwards, they can scientists have did a lot of analysis, and then on these common narrow speeds, where they understood that the amplitude, once it reaches maximum amplitude, the failure can initiate. So how we can stop these maximum amplitude, or the how we can reduce its maximum amplitudes. So that's what their major focus. Then they introduced one term called as the damping. So by using these damping, we can able to reduce the maximum amplitudes. And even though it goes to the maximum or the resonance condition, but if we have a damping, then obviously the system or the structure won't fail. So that is the basic understanding made from this Tacoma narrow speech failure. So then onwards, how we can go with a high rotating or the rotating machines where it always crosses its natural frequency. So then let us say the system, just one example I am telling. Let us say one system is having a natural frequency, maybe a some 100 radians per second, but maybe we need to rotate that one with a some 200 or 300 or 400 or 500. So then you know that once it reaches its resonance condition, obviously there is a large amplitudes will happen, and due to these amplitudes will causes the failure in the system. So then how to stop this one? So by incorporating one damping mechanism into a particular system or a particular material, so that we can able to run these one less than these maximum amplitudes, then obviously the system won't fail. So for that, how these damping elements are there, and what are these various damping elements, we'll see later. And before that, just we'll see what are these mass elements, and in the mass elements, how the discrete masses and the body perspective, as well as the point masses. Point of you'll see is a discrete masses. Let's say it is a point mass, then T is equal to half mp square. Then let's say it is a rigid body, then we have a translation and the rotation. Stiffness of a spring. So the stiffness is nothing but a force needed to make a unit displacement. So how much force we need, that is called the spring stiffness. So here the spring, which is a linear spring, then obviously we need more force to have a more deflection. But if it is a hardening spring, then once it reaches certain displacement or the deflection, then obviously it will become very hard. After that onwards, you can see from here, if you want to make a small angular variation, so you need a very high force. So this is the amount of the force we need to incorporate here. So once here you can check, so here it will increase. So like this way, for each unit deflection or the small deflection, we need very high force to make a small deflection. So in the same way, I mean, the contrary to these hardening, a softening spring, where the deflection will be very high, but force need is very less. It is the softening springs. These are the three types of the spring behaviors once we are using these springs for the long time. Then how these energy stored equation we can keep in terms of a stiffness, they're half k del x square, where these equations are very important to us for a structural analysis. So then the stiffness doesn't mean that always a spring should be there and it will have a stiffness. No, it's not like that. Just for a simple case here is one rod, we know the stress, we know that the stress which is equal to Young's modulus E epsilon, where this epsilon we know that del L by L, and where the sigma which is equal to P by A, and E del L by L, del L by L. So where this P by del L is a nothing but a stiffness, and if you move this A to this side, then we'll get EA by L, where this P by del L, that is nothing but a force, force need to make a unit deflection. Anyway, the stress is nothing but a internal resisting force that I am assuming this as a equivalent to the external force. That's what I mean to say here. So P by del L is nothing but a external force needed to make a unit deflection called as a del L is nothing but EA by L. So this is the stiffness of any system or any object or any point. So here for various other systems, we have taken this stiffness. So many of you already know these points. I'm trying to correlate these aspects with the composite equation of motion, or deriving these equations of motion, so that how to connect. That's what I am going to do here. That's why I am going very somehow more quicker while I am not deriving any equations and all, as I am assuming that already all the people are know these things. If you are unable to follow this one, please let me know. So damping elements, here after the Tacoma narrow spirits failure, measure the damping element importance have understood, and then in real life the systems do not vibrate forever. If they do, there should be something pumping energy into that system. So these energy initially associated with the oscillatory motion and gradually converted to heat or a sound. So these absorption will be done by this damper called the damping mechanism. So here we have a three types of damping mechanisms. It is viscous damping, Coulomb or the dye friction damping, material or the solid or the hysteretic damping. So viscous damping, the experienced by the system vibrating in a fluid medium such as air, oil. The resistance offered by the fluid to moving body causes the energy to be dissipated. So the amount of energy dissipated depending upon this fluid, as we know that this viscous properties and viscous fluids in between the two parallel plates. I'm not going to derive these equations again. The force which is equal to CV. Then these stories, these equations from the fluid mechanics you can refer. Newton's law of viscous flow. Then according to this constant called as the damping coefficient, C is equal to A by H. And next one is called the damping through friction. So here a damping force is a constant in the magnitude and opposite to the relative velocity between the bodies in contact. So majorly here the rubbing of a or the drying or without sufficient lubrication, it will generate this friction, and due to this friction its motion is lost, and that motion is converted slowly into a heat due to this friction. So that way it is dissipating its motion in the form of a heat by friction. So here we can see here so in this case, let us say I assume there is a some friction force is there. So this friction force which is equal to mu F is equal to mu n. So the system is moving in this direction. So this is the x. Sorry, this is the x. Then obviously the spring stiffness, this spring force. So acting opposite to this is nothing but the kx, and body is moving in this direction. So obviously the friction will act in this direction. So that friction force which is equal to mu n. So where this n is the normal reaction. So here we are assuming this n is which is equal to W. So then by according to Newton's second law, sum of all the forces which is equal to effect of force. The effect of force is nothing but m ax. So these x, then obviously it will have a x dot. So x dot, then x double dot. So these are x double dot. I am considering this as a sorry. I am considering this as a ax. Sorry, my digital pin is not working that much properly. Please bear for this. And mx, this side we consider this as a positive force, is a positive, and this one as a negative. So minus kx minus fn is nothing but mu n to n. So this is minus kx mu n. So this is a sign of a sign depends upon what is the frictional force direction. So this is how we can give its free body diagram. From the free body diagram, through Newton's second law, equation of motion. Then damping through the friction. So finally we can get this displacement in the form of a cos omega nt plus b sin omega nt plus f by k. F is nothing but this friction force. So then next one is the material or the of solid or the hysteretic damping. This is nothing but the material itself will have certain damping mechanism or the damping property called the energy absorbed and dissipated by the material itself. So this is nothing but already we have seen stress strain diagram where say I have applied a force like this way and it is deformed, and now you try to release this force. So will it follow the same line? No, it will follow the different line. So there will be some strain energy will be there. So that's what the same thing here. If I apply a load and I release this load, unloading, the material will absorb certain energy. So this is nothing but a hysteretic damping, also called the solid damping of a material. So here it will follow a loop called the hysteresis loop. Then with these, what are the three major elements for or the vibration is nothing but a mass, stiffness, and let's say damping element. These three damping elements we have seen. And then now we need to understand a system is having a how many independent coordinates or the states to uniquely specify or to specify that particular system or a body. So here with a single degree of freedom system, that means only one coordinate is needed, or the independent coordinate. Not it's not like a dependent coordinates. Like you take a oscillating member, all these. Take a bob. Sorry. So here x and y, the displacements will be there, but these x and y displacement cannot be taken. The theta only, this angle. So this theta is the independent coordinate. The x and y cannot be a coordinates here. The only the one independent coordinate called theta. So that is a major difference between the independent coordinate and the coordinates to represent a system. So uniquely specify the position. So it should be uniquely specify. So this will uniquely specify. Hey, whereas here, if let us say these x and y in this direction. So there is a from this position, then obviously, so from here to here, some x will be there and some y will be there, but they are not the independent coordinates. So here the only one theta is needed to define where is its location. So then it is called the single degree of freedom system, damped, undamped, free vibration, forced vibration, and multi-degree freedom system, same damped, undamped, free vibration, and the forced vibration systems. So here for each type called damped, undamped, free vibration, and the forced vibration, how the equations of motion can be derived and can be solved. So that's what we'll see. Then we'll see the same thing to the composite cases, for the composite structure cases. The first we'll do for a single degree freedom systems, where it is a very easy to understand. The people can follow very easily. So this is a model where one particular system I have converted or represented in the vibration modeling called M, and here as we know that this is K, this is C. So resonance, a vibration of the large amplitude, occurs when the object is forced near its natural frequency. So this is one vibrating washing machine. So this we can model in a form of a KMC, where there is one mass. Here the mass is oscillating. So that's why this is the mass. Maybe some clothes or something we keep here, and then it will oscillate, rotate inside this. So this is a case where a system with a rotating mass, and the system itself will have a one mass, and then there is a external member will add, and that also will oscillate. So then this is the concept of the vibration absorber, where it will absorb whatever the vibrations induced by major primary system, and this is the secondary system. It is the vibration absorber. By keeping these one, the vibrations of these particular one will be there. You can see these, I think Burj Khalifa, you can see this example where the vibration absorber will keep by taking one more mass. So chosen these to eliminate the motion of an object. Then various vibration absorber example. Then here come to our major structural analysis. Here we need the mode shape, resonance, and natural frequencies. So these resonance part we have seen where when we'll get the resonance condition, and what is mode shapes and how these natural frequencies that we'll see in the next. These are the three characteristics we need, or characteristic geometry of a vibration. So for any vibration analysis procedure, as mathematical modeling, nothing but first we can convert that physical object into a vibration model, and then we can represent that in a mathematical form. That mathematical form is nothing but a governing differential equation, and solving that governing differential equation, and we can interpret various results. So these are the 4 steps to be followed for vibration analysis of any structure. So how these structures can be broadly divided? These structures can be broadly divided into a discrete parameter systems, and then is a distributed parameter systems, or the continuous parameter system. So here, how many degrees of freedom will play a very important role. If you are able to say what is its finite degrees of freedom, then obviously it is a discrete or the lumped parameter system. Then distributed parameter system, where if you are unable to define its particular system with a one finite degrees of freedom, then we'll call this as a distributed parameter system or continuous systems. So in a mathematical perspective, the governing differential equations will follow the partial differential equations, whereas here ordinary differential equations. So here with the ordinary differential equations, after solving, we can get this one as a mx double dot plus cx dot plus kx, which is equal to fp. This is a generalized form, whereas here we got these partial differential equations, and these equation here we can see there is a t, and this term after solving we can derive its forces, where the boundary value problems by using the finite element formulations, or in the starting days we solved by using a numerical methods. So we solved these equations, partial differential equations. After solving these partial differential equations, we will find elements called what is the m, what is the k, and what is the c, then what are the forces acting on this one. So after combining these everything again, this discrete system also will come in the form of a simple equation. So then we can make our vibration characteristics called the mode shapes, then what are the natural frequencies. So these elements we can find out from here. So that's how we can identify what is its structural behavior. Then how we can, the type of these mathematical problems in the vibration. The lumped systems lead to the ordinary differential equation, continuous system lead to the partial differential equation. So as we already seen, these are more difficult to solve these. The typical problems, not only that ordinary linear, and these are the non-linear. So lumped one and the free and the forced vibration. So these are the ordinary differential equations itself. There is a non-linear term once you take the time, and without taking a time is the linear things, the free and the forced vibration. So whereby by taking these non-linear and various hypotheses, that will give us very true or the very nearer values of these analytical results to the practical values. Then these are the few examples where you can identify what are the linear equations, what are the non-linear equations. How to solve these one particular equation of motion, Newton's second law of motion, a typographical error. So this is Z, this is Z, so please change this one. This is Z, it is not the Y. Then normally many will get confused that it is a linear translation under the rotation. The rotation under the translation, whatever it may be, the Newton's second law is same. So some of all the forces is equal to the effective force. So here sum of all the forces sigma m naught, which is equal to I naught omega naught. Then this is the energy formulation where kinetic energy perspective in the rotation of I. Then this is the mass moment of inertia and parallel axis theorem and perpendicular axis theorem already we know that. And general planar motion. So we'll get this equation of motion. And then energy approach to derive the derivation of a equation of motion. So whereas this Newton's second law method will be very useful for a simple single degree of freedom system or the multi systems. We can't go with these, whereas we need to go with the energy equations only, or the energy. Where according to the conservation of energy, total energy is constant. Then obviously the change of energy or the change in energy, which is equal to 0. So from that T1 T2 minus T1, which is equal to U2 minus U1. So obviously it will go like a this one. So T1 plus U1, which is equal to T2 plus U2, or sum of energy, which is equal to constant. For a non-conservative systems, we have a then equation of motion for the spring mass system. This is the simple equation where the natural frequency, how to find the natural frequency. If you know stiffness and then mass of element, so irrespective of this is whether it is a lumped system or a continuous system, whatever it may be, if you know the K and M, obviously we can find natural frequency. We can find the natural frequency. So the general equation or the general solution for this, and then the free vibration of undamped torsional systems, then we can get natural frequency, which is equal to torsional stiffness by J polar moment of inertia. These are the two. So whereas there we got a stiffness by mass, whereas in the rotational terms we can give the torsional stiffness and then the polar moment of inertia. And these are the time, the natural time period, and then the frequency in hertz. And these the bottom are the solutions for this. Until now we have seen only the without damping. Now let us say if you have a damping term called Cx dot, then how to solve this one? Xt, which is equal to C over Ht. So mx square plus Cs plus k, which is equal to 0. Where these in terms of the transfer function we can form, or for the solution we have represented in this form the Laplace transformation case or the roots s 1 comma 2. Here itself we can divert these areas or these equation of motion to a control system perspective, but anyway we are not going to discuss about those perspective. We are simply solving only the equations here, the root of which s 1 comma 2, and we can get the solution in this form and xt. Then from here we got, I am not going through these derivations as we already have, as we already know. I am not going detailed discussion on this. So this is nothing but a critical damping coefficient, so which is equal to 2m omega n. Then zeta is nothing but a damping ratio, which is equal to C by Cc, critical damping coefficient, by the normal damping coefficient. So after solution, this one, and there is a various motion taxonomy is there, and which represents, so zeta which is equal to 0 is called as the undamped one, and greater than 1 is called as the overdamped case, and it is a damped case, and it is underdamped case. So undamped case where we can get the solution x and total xt, which is equal to a e power st. Then damped motion, here we have a two cases where called as the underdamped and the overdamped and the critical damping case. So it is called the overdamped case, zeta which is equal to greater than 1. It's called the supercritical where aperiodic motion will be there. So there is no repeated motion will occur, as well as the motion where if you give some motion to or the displacement to it, so it will come to its original position very quickly and it won't travel in the opposite direction. So that is a over damper or the supercritical one. Always these shock absorbers and whatever we are using for the door applications and all, normally with a over damper case. Then critically damper case where it will take some time to come to its original position, but as well as here we can understand it won't repeat. And here is the under damper case where zeta is less than 1 case. It is also called the subcritical case. So here there is a oscillatory motions will occur. That's why it's called the periodic motions here. Whereas critical and a over damper cases are the aperiodic. So the periodic case is the under damper case, where with these over damper case, these are the various applications. Door closer will and all we'll use here. Then these are the over damper case. Then zeta which is equal to 1 is a critical damping case. So if you use a critical damping case, let us say its C term is reduced, then obviously it will go to the under damper, under damper case. So that's why normally we won't prefer critical damping case. We'll always go for a over damper case. Critical damping case, it will take some more time. So this is where under damper case, beta which is equal to less than 1, where how much damping we can apply here, and damper frequency, the natural frequency, these relations. Then the damped time period, damped frequencies in terms of hertz, so these are the under damped example case, and then the graphical representation of the system response under damper case. So these are various where you see zeta which is equal to 0. So it oscillated normally. The same system. If zeta is equal to 0.5, we can see. So this one oscillation only there, green color, and zeta which is equal to 1, and it came to the position very slowly. See here, there is a some. No, this is a zeta 1.5. This is zeta equal to 1 case. Then this is a logarithmic decrement. Again, I'm not going to the derivations of this one. So through logarithmic decrement, what is the major purpose of a logarithmic decrement is to how much amplitude of vibration is reducing from one cycle to another cycle, and how this term is related with the, so how much is reducing, then how this term is related with the and zeta. So this is the major important aspect here. Once zeta changes, obviously the logarithmic decrement, that means the how much amplitude of vibration is reducing for the each cycle will also varies. So zeta which is equal to L by 2.5. Then energy displacement we discuss. So once we take the case of called the viscous damping case, most of the cases will take the viscous damping only, because it is more efficient when compared with the dry damping and the friction damping and the material. So then total energy in the damping term, energy dissipated. So this is the last question. Also called the loss factor, energy dissipated. How much energy is dissipated? So natural frequency 1 and the energy dissipated, how much loss coefficient is there? So these are the two major factors which will decides how the structurally stable a particular system or a model. Then torsional systems with the viscous damping. This is one example where, because previously we have seen the linear vibrations, now we have seen the torsional vibration. Then free vibration with the Coulomb damping, how it can be equations of motion. Because we have seen the viscous damping, now by using a Coulomb damping, how it will reduces. Then the torsional system with Coulomb damping. The Coulomb damping only the equations are given, final result, final equations. Then the free vibration with the hysteresis damping. How this is related, and hysteresis case. And the complex stiffness. Then again, damping ratio and the logarithmic decremental, and this equivalent damping constant. So with this, the free vibration, free vibration is a vibration where only the initial time the force will apply, and after that the force will be, that is called as the free vibration, where the force vibration is after a repeated interval of time, so will apply the forces, then it is called as that forced vibration. So normally this magnitude or the amplitude of this force will be constant, and where this time will be different. So how it is behaving is will be varies, like cos means in the initial time, observation time, it is at the maximum peak. Then cos, if it is a like 0 it start, then sine, or you can take for the mathematical equivalent is e power I omega t also. So here there is no phase. So whatever our observation and the maximum displacement or the minimum displacement are the same here. So f naught cos omega t. So then in this case, how to solve? So here one more term we got. Normally we got only this term, but we got this extra term also, this particular solution called steady state solution and the transit motion. So these are transient solution, and these about our steady state solution. Then this is a combination. The same thing we can, maybe the transient condition cannot be like this, it may be in this manner also. So it may be increasing with the time. So that, then in this case, how to solve these one solutions? Then the forced harmonic vibration, where these harmonic vibration cases are very much useful to us in the structural vibration analysis. So here it is subject to a force, and this force is a harmonic force. Then mx double dot plus kx plus cx dot, which is equal to f sin omega t, and this is the displacement term. Then dynamic load factor, also called the amplification factor. So amplitude of the forced vibration by the static deflection. These are the solution cases where we got the two solution, then G ratio. So this is very interesting observation, where we can see here it is the natural frequency is equal to the forced frequency. It is the our resonance condition. In the resonance condition, we can observe these the amplitude ratios. This is the static deflection, and this is the deflection. So the static deflection when compared to the static deflection, x is very much high. So you can observe here. So this is the nearby these. And sorry, this area is a near to natural frequency, where we can observe the amplitudes are increasing like anything. So these amplitudes, if you are not reducing, then obviously the system will fail. So here the system, you can observe there is a failure. That's what happened to the Tacoma Narrows bridge case. So even nearer to the natural frequency, it is need not to be go to the very exact to the natural frequency. Then by applying a one damping term or the one damper, so we can able to reduce its amplitude much lower. And so once it subjected to these one, it will have a oscillations, but it won't fail. But maybe that oscillation may create some sort of the noise, or maybe the discomfort may be happen, but definitely the system won't fail. So this how here now we can observe it is the first natural frequency. So we got to the second natural frequency. So here you can observe there is no sound, and this is the third natural frequency will come about here. So this is called the first harmonic, second harmonic, third harmonic. This is also called the harmonics. So this how we can able to rotate any one member with a more than its natural frequency. Then obviously we can understand that the systems can be rotated with the very high velocities or the very high rotating speeds by applying or by keeping one more object called the damper. So this is the case where only mass is subject to the harmonic force. So mass is there, stiffness is there, damping is there. This could be any system. This is just only vibration model I am showing, but actual system we don't know. The same case, let us say the phase angle. What is the phase angle perspective? How the phase angle is being changed with respect to the natural frequency. That's what we can observe here. Then if you want to go for a vibration isolating medium, what is this vibration isolation medium? That means whatever the vibrations are happening here, that should not be transmitted to the base. So if you want to make like that sort of systems, how should be its behavior? So you can see here, okay, omega by omega m, frequency ratio. And then this is the transmission ratio, how much force transmitted to the originally force applied F naught. So this is about the vibration isolation case. Here also again at 1, there is the root 2 case, there is a major phase change is there. Major phase change is happening here. So that is called the vibration isolation case. So here we can able to reduce its vibrations. Force transmission. So here at root 2, we can make this force transmission same. Almost at greater than root 2, we can say that obviously the force transmission will be very, very small. So while designing, we should take these points into the consideration. So then support motion, if the support is also moving with respect to the major, the member of the system is moving as well as support is also moving. In this case, how the relation is going to. So here again, root 2 is the major case. Ratios and then the displacement ratios. Then the rotating unbalance. So if you have some unbalanced masses, washing machine case we already see. In this case, how the system again here also we can observe with the damping we can able to reduce its oscillations. So this way we can able to. So these are the one rotor unbalance. Okay, before going to see, just to summarize here. Now we have seen a vibrating member and what is its motion and how the vibration can be characterized by converting into a vibration model called mass, stiffness, and damping term, and what are the importance of damper and what are the importance of amplitudes. So once we know the importance of amplitude, then obviously we can understand that importance of damper. once this damping, how the equation of motion is going to be changed, and what are the various equations of motion can bring. And here, what are the 4 different cases is normally possible, is nothing but the system and which is subject, having this stiffness and damping term and subject to a harmonic force. What are the design criteria should be there for a vibration analysis perspective. Then transmission by vibration isolation case, how we can design. Then rotating unbalanced case, how to design. Then again base rotation is there, or the base oscillation is there. In this case, what are the critical conditions to reduce its amplitudes. So these are the 4 different cases. These don't check or don't see these things even only for a single degree freedom perspective, because the single degree freedom perspective, these are very easy to understand. But whereas if you go for a lumped systems and then the continuous systems also, we can apply in the similar concepts. But not similar concept, the solution will be the same, but the only thing is that we need to bring that into a particular form called as the mx double dot plus cx dot plus kx, which is equal to f. In the term, if you are able to bring it, then we can solve this one. So how to solve that one, I will discuss in the next cases. This is the rotor unbalance, where the static unbalance case, where in the only one plane the unbalance is there. Then there's a dynamic unbalance, where there is a 2 plane unbalance are there. Then whirling of the rotating shaft. There is a various reasons for whirling: eccentricity and mass, hysteresis damping in the shaft, fluid friction in the bearing, viscous damping. So this whirling of the rotating shaft we can observe if we have this laboratory experiment. You can see this first natural frequency mode shapes and all, first mode shape and second mode shape, and 2 degree freedom system, where this we have taken one simple pendulum case. It's a double pendulum. Then here theta 1, theta 2 are the 2 degrees of freedom, where the x1, y1, these are the dependent coordinates. So the same way we can take these masses, how the equation of motion. Then this equation of motion we can represent cx dot plus kx, so in the matrix form. So that's what we need to understand here. This is where here square bracket for the matrix and curly bracket for the vectors. Then various nomenclatures. So this way, I am not going very detailedly how to derive these equations and all. Displacement factor, force factors. Then final remark, we can hear the matrix notation. So here, how to solve these one in the matrix perspective is called as the matrix A singular. Then free undamped system, where F will be 0. So by taking this free undamped system, obviously we can find the natural frequency of this. So this way we can find the natural frequency, determinant of it. So then the solution for the natural frequencies will be this one. These are the 2 natural frequencies, because this is 2 degree of freedom system. Obviously, got the 2 natural frequencies. If plus is minus 1, so minus will be a smaller one. That's why it is called omega n square 1, and plus will be a second natural frequency. These are the 2 natural frequencies we can get from here. Then these natural frequencies, we can take the ratio of these amplitudes with the particular natural frequency. Then we can get here one eigen vectors. So these are the eigen vectors we can get with R1, R2 by substituting 1, and 1 will get 1, and by substituting another one we'll get R values. And these vectors, eigenvectors, is a modal vector or eigenvector 1. Then for the second natural frequency 1. So the solutions can be expressed in this form. Then initial conditions. Then solving this one, we can get angles as well as the vectors. If you draw these one in a particular shape, that is called as the mode shapes. So the solving can be expressed in the matrix vector notation. These displacement we can represent in this vector form as well as the time function. So this is one example. This is self example. You can solve. You can take this as a one example and you can solve it. And next one is the multi-degree freedom system. So before we have seen the 2 degree of freedom system where we can solve these individual equations very easily, whereas to solve these multi-degree freedom system we need some finite element formulation methods where we can say the influence coefficient. Influence coefficient is nothing but a reciprocal of the stiffness is nothing but a influence coefficient, and flexibility influence coefficient to solve is multi-degree freedom system more than 2. Stiffness influence coefficient, you take this as an example case and you can solve it. And this is the stiffness influence coefficient. So these are the ways how to solve the multi-degree freedom system problems. And this is the final flexibility and the stiffness coefficients. Then these one MATLAB question that we'll solve in the afternoon session. Then now we have seen the vibration perspective, the vibration for the system with a single degree freedom system or multi-degree freedom system, and how, let us say, this member is failing, how, what are the various theories are applicable. That's what the failure theories. I will combine that concept with this now. The vibrations in the design perspective, types of the loads or the stresses, the theories of failure, normal stresses as you already know, then shear stress. So any member can be subjected to only 4 different types of the stresses: normal stress, shear stress, and bending stress. Bending stress. And then this is the shear stress, torsional shear stress. So this is one member, one element is subject to the forces, and this is about the one plane. If you take, and then principal stress, how to calculate this principal stress, and this is the way how we can, by using more circular method, find maximum principal stress and minimum principal stress and the maximum shear stress. And the various theories of failures, majorly 2 groups. One is the elastic failure theory and yield failure. Then excessive elastic deformation is called elastic failure, and yield failure is excessive plastic deformation. These are the various examples, and then the modes of failure perspective: elastic deformation, general yielding, and fracture. Then these are the 5 different types of the theories of failure: the maximum principal stress theory, the Rankine's theory, maximum shear stress theory, or the Coulomb's or the Trescos theory, maximum strain theory, also called the Saint-Venant's theory, Huber von Mises and the Henke's theory, and the maximum strain energy theory, also called the Huygens theory. And the failing factors perspective, on the stress principal or the normal stress theory and shear stress theory, and where the strain perspective is the principal strain and energy, maximum strain energy theory, and the shear strain energy theory. So these about till now there is a basic things what we already read. Only the gist of that I took and needed for solving the composite problems, composite and the smart perspective also. So now we'll come to the main topic called the 3D elastic element. So this 3D elastic element, as you know that the x sigma x is nothing but tau xx, tau xy. That means tau x will indicate here. X indicate the plane and y indicate the direction. So you can observe your tau x. It is the plane perpendicular to the x-axis is called tau x. Y is the direction. This is the y direction you can see here. This is the y, and this is the z direction z. Direction z and x. So tau x y and tau x z. Z is the direction. So the same way here tau yy is nothing but sigma y. Then tau zx. Tau zx. These are tau. Tau y z. This is the tau yx. Tau yx. So the same here opposite will be there. These elements. Also this one tau yx and tau yz opposite to that active. So opposite action is indicating it is in the equilibrium. Like you see here, sigma y, and here it is also sigma y. So then both are same. Then tau yz in the one layer and opposite layer tau yz in the opposite direction. So both are equal. So in this way, this plane is also will have a subject to a equal stresses, and again this plane nothing but opposite to this plane. So there is a 6 faces are there, or 6 planes are there. All the planes will subject to a equal amount of the stresses in the opposite direction. So that means it is in the static equilibrium condition. So once it is in the static equilibrium condition, by applying this conservation of linear momentum, we can write these sigma and rho g. So these are whatever, these are the 3 static equilibrium equations by the conservation of linear momentum. Then constitutive equation, second one, constitutive equation by the material response to the stress or strain. So in this perspective, we have a 6 constitutive equations or constitutive equations. Then alternatively, the strain stress equation. Then next third one is the geometric relations or the kinematic for a small strain. For a small strain, we have these geometric relations, kinematics for the small strain. These are the 6 equations again. So the total one 3D element is having 15 equations, 3 equilibrium equations by the linear momentum, and 6 constitutive equations, either stress strain or strain stress. Then 6 is a kinematic strain equations. These are the strain function of a displacement gradients. So 15 unknown variable stresses are there. So this will vary according to the material that already you might have already discussed in this few days. From Monday onwards, you might be many guests might have discussed all these things in the composite, various types of the material with the anisotropic material, isotropic material, then orthotropic material, and then transversal isotropic materials. So according to that, then anisotropic material will have all the things, and whereas the isotropic, then some few elements will go. So like this way, the total these 15 governing equations we can solve, and by these solving only, by solving this one based on a particular assumption or a particular material behavior, we can solve this one. So this is a broader perspective I'm telling. Then we'll take the particular cases. Then we need the boundary conditions to solve these boundary value problems. Then here we'll take a special cases called a plane stress and the plane strain case. First we'll take the plane stress condition, where if a member is a thin, then obviously we can take this plane stress condition, where this in the z direction, sigma zz, sigma xz, sigma yz terms will be 0. Then stress tensor will reduce to sigma x, sigma xy, sigma xy, sigma y. So these are the sigma x6, sigma xy. Then z term, as it is very thin, then there is no z term. Then this 2D. Now how these 15 equations will become? The static equilibrium equation will become only 2. Then constitutive equations will become only 3. Then strain displacement equations will become 3 again, and then they will have a compatibility equations. So like this way, a plane stress condition will be there. Now we'll take the plane strain condition, where this is the body force will act here in the plane strain condition. So this is about the plane strain condition. I am not discussing much detail into the plane strain condition. Normally these will go for this plane strain condition for the more thicker materials. So in this case, the z direction also forces is there. You can observe here the z. And laminated composites. Now we'll come to the composites. So these are the laminated composite. It is a reference plane. There is a various number of laminas are there. Then we can observe here, once it's get deformed, z direction, x direction, y direction, then Rx, which is nothing but 1 by Kx. Kx is the curvature. 1 by Ky, nothing but radius of curvature R by Rx. Then these are undeformed reference planes, and these are the deformed cases in a x, y plane, and then the xy plane here we can see the deformed reference planes FD, and the total Kxy will become like this way, and whereas here Kx, Ky which is equal to 0 here. This is the laminated composite case, and this composite case I have taken only a, here I am representing in the transverse direction, whereas if I take in the another one plane direction, where maybe the xz direction. So here it is the xz direction, x, whereas here it is a xy direction as you. Then these are mid plane. This mid plane dimensions will be same, where the top and bottom dimensions will be varying. So how much it is got deformed is based on dou w naught by dou x is nothing but gamma xz is nothing but the this diff. So here you take here. So up to this it is a u naught. This is my reference. This is my reference, and it got deformed by these. So these are the deformation. So once it get deformed, this is the my midterm mid plane deformation is called u naught. U naught is my midterm mid plane deformation. And if you take this point, then this is nothing but what is this angle. So you can observe here how much this distance. So this distance is nothing but angle multiply with this distance. So we already know one concept. So let us say this is a theta, and this is r. So what is this z or something, whatever it may be. So we can take this is equal to the yeah. So So this distance is nothing but r theta. R theta. So this is the r theta. The same way here, from this to here, this distance is nothing but a z, and angle is nothing but dou w naught by dou x. So that's what this distance. So u naught minus z x xz is nothing but they took the point here. So this point this point definitely will have a slight variation. So this is nothing but u naught minus z dou w naught by dou x. So this is the u value. This is my u value. And epsilon x dou u naught by dou x, epsilon y naught. So naught will represent for the mid plane, and gamma xy naught is nothing but dou u naught by dou y plus dou v naught by dou x. So this is the u, and similarly the total displacement in the y direction is v naught minus z dou w naught by dou y. These are the these about zy direction, zy plane, not in the xz plane. We have represented here u, and yz plane v will be there. So then we can write gamma xy dou u by dou y plus dou v by dou x. So this is called as the classical laminated plate theory or the beam theory. So epsilon x, epsilon y, gamma xy, epsilon x naught, epsilon y naught, gamma xy naught plus z kx, ky, kxy. So these are about the strain equation. And these are the forces which are acting on this plane, normal forces and the moments, and then the shear forces V. So the combination we can write these in terms of shear forces tau xz dz and Vy tau yz dz. So nx, ny, nxy, mx, my, mxy. Then this sigma x we can write in this manner. So A, B, D matrix, nx, ny, nxy, mx, my, mxy. So we can write this total ABD matrix. So here you can apply whatever the boundary condition you have considered, as well as the plate material property, whether it is a isotropic or whether it is orthotropic. This is the basic equation for a one composite laminate. So then we have to, by taking simply representing these in the forces and then movements and stresses and strains and displacements, we can't solve these one. We need to solve by taking into the energy formulation, where from this energy we can get the stiffness and the mass matrices. Those stiffness and the mass matrices, we can take the ratio and we can find the natural frequency. First we'll take the strain energy. Strain energy U is equal to half integration. So then we can represent in this manner, and this is the kinetic energy. From the kinetic energy we can get the mass. From here we can get the stiffness. So from here, this strain energy we can get the stiffness matrix. From the kinetic energy we can get the mass matrix, and the natural frequency, which is equal to root of stiffness by the mass. So in this way, for any composite structure, either the beam case or the plate case or membrane cases or the shell cases, we can find the natural frequency. So for finding these displacements, and then these all related with the what the theory you have considered. So here it is the classical laminated plate theory, CLPT. So that's why it is only there one strain will be there, but where the first order shear deformation theory, if you take, then that terms will be increasing, and if you take a higher order shear deformation theory, then some more terms will be there. But whereas the basic flow will be the same. So this is how the one structural analysis, finding the natural frequencies of a composite structure can be taken place. And the same way we can find its damping properties also. Yeah, that's what I like to say. So these are the various references: mechanical vibration by S.S. Rao, solving vibration analysis problems by Rao V. Dikupati, and design of machine elements by B.B. Bhandari. He is a professor from aerospace engineering, Walter Heisler. So his material also I referred, and mechanics of composite structures by the L.P. Kollar and G.S. Springer. So these are the various references I refer for making this PPT. Thank you all of you. So any doubts, please. Any doubts from the participants?
Hello. Sir,
Hello,
I'm
madam.
audible.
Yes, madam.
Any doubts in the session, participants can please pose them. Hello.